Joyce Guzik is a laboratory fellow in the Theoretical Design Division at Los Alamos National Laboratory. She received her PhD in astrophysics at Iowa State University in 1988. In addition to her programmatic work at LANL, during the last 12 years, she has been working on analysis and modeling of pulsating variable stars observed using the NASA Kepler and TESS spacecraft. All right, over to you, Joyce.
All right, can you see my screen and can you hear me?
I can hear just fine. I think you're in good shape.
Okay, if any time something cuts out or you need me to change some settings, let me know. So I'm keeping my video on, but if the bandwidth is low, I can try to turn that off. All right, so thank you, Rick, for that very nice introduction. So I'm going to be giving you a talk today that I haven't given before. And I didn't think that a year and a half ago, I would be working on this variable star cluster. This is a kind of an obscure variable star cluster, as you will find out. But I ended up getting into this because I was asked to write a review paper on delta Scooty variable stars that were observed by Kepler. And the editor of that collection of articles was my second author here, Andy Barron, and he's from Poland. And he contacted me after I had the paper accepted and said, I have this data from Kepler on the star cluster, and it's a really unique data set. And I find stars in it that might be delta Scooty variables, but I don't know anything about these stars. And would you please take over the analysis and the writing a paper about these stars? So I said I would try. It's turning out more that he's doing most of the work and I'm just asking questions. But in the end, I hope we'll have a paper out of it about the variable stars that I'm familiar with anyway in this cluster. So the other two co-authors are one of his students and another colleague from the Czech Republic. So, you start one thing and it gets you involved in collaborating with people on the other side of the world. So this star cluster, NGC 6819, is an open cluster as opposed to a globular cluster. A globular cluster was formed near the beginning of our galaxy's formation. Those could be 10 billion years old, but these open clusters aren't that old. They're more in the disk of our Milky Way Galaxy. This cluster is in the constellation Cygnus the Swan, and it was discovered by Caroline Herschel in 1784. It's quite far away. It's 8,000 light years away. Some of the stars are closer, some of them are further than that, but on average about 8,000. Its age is 2.5 billion years old. So it is half the age of our sun. So a lot of the stars in this cluster are a lot young. Well, they're all younger than the sun. They're all about half the age of the sun. And the brightest stars in this cluster are only 10th to 12th magnitude. Naked eye, we can only see down to about 6th magnitude. So Caroline discovered this cluster using a telescope. And if you wanted to see this today, you would need a telescope or binoculars to pick out some of the stars in this cluster. So I'd like to tell you a little bit more about Caroline Herschel, because she was really a remarkable person. She lived to be almost 98 years old. Her brother, William Herschel, was maybe more famous at the time. He was an astronomer. They both moved from Germany to England, and William Herschel was pursuing a career in music there, and Caroline joined him, and they were doing, he played organ, he was a church musician. Caroline took singing lessons and harpsichord lessons and became an accomplished singer and harpsichord player, but she didn't want to perform with anybody else but William, so her career was limited because she wouldn't take any more singing opportunities if she couldn't have William with her. And then William got interested in astronomy. And so she followed him into astronomy, and they made their own telescope and they did a lot of observations. Carolyn, you can read about her in Wikipedia. There's a really great article there. She was the first woman to receive a salary as a scientist. She was the first woman in England to hold a government position. She was the first woman to publish findings in the Philosophical Transactions of the Royal Society. She received a gold medal of the Royal Astronomical Society in 1828. And she discovered many comets as well as these clusters. And she arranged 2,500 nebulae and star clusters. Many of those were known before, but some of those she and William had discovered. She arranged them into zones by polar distance and made a catalog. And this became the predecessor of the new general catalog, which is why this cluster is called NGC, for New General Catalog, and with the number 6819. So why do we study open clusters? Well, what's really useful about them is that all the cluster members should have formed together as the gas cloud collapsed and broke up into these stars. And therefore, all of the stars in the cluster should have the same age, and they should have the same element abundances of helium, oxygen, carbon, nitrogen, and all the other heavy elements. They should be the same, at least when the stars first formed. And knowing the cluster age and the metallicity, basically the element abundances in the stars, will give additional constraints for stellar evolution modeling and for this field of variable star research that I'm involved in called astroseismology, or using star waves, star quakes, acoustic modes, gravity mode, pulsations, to try to figure out what's going on the inside of the star. So you are probably familiar with some open star clusters, not NGC 6819 necessarily, but probably the Hyades and the Pleiades. The Pleiades is an open cluster in Taurus. It's often also called the Seven Sisters, and it's you can see it up in the upper right of this picture with these very bright blue stars. This is a very young cluster. And down here below, there's kind of a V-shaped set of stars in the constellation Taurus, and this is the Hyades. It's also visible naked eye, and it is not as young as the Pleiades, so it has more yellow and red stars, but it's pretty young as well. So what astronomers have done is that they've taken a lot of the open clusters in our galaxy, determined their distance and the absolute magnitude of the stars in the cluster, and put them on this magnitude color diagram. So for example, let's see, here's the Pleiades. All of the stars in the Pleiades line up on this line right here on the main sequence where the stars are burning hydrogen into helium. So where they are starting to evolve off the main sequence and become red giants, this is called the main sequence turnoff. And by finding that turnoff, you can use that location plus stellar models that we call isochrones, basically sets of stars of different masses with the same age, to determine how old that cluster is. So here for the Pleiades, you see this 10 to the 8th, so it is 100 million years old, the Pleiades. And then if you look down here, the Hyades are down lower. The stars that are brighter and burn their hydrogen into helium faster have already moved off over here to the right and become red giants and whatever else they're going to do, white dwarfs. But the Hyades turnoff is over here closer to 1 billion years. It's actually about 600 million years old is the age of the Hyades. And the cluster Chrysope is very similar age. So the oldest star cluster, by the way, that we have on this graph is M67 right here. And it is actually about as old as the sun. And there was even some speculation that the sun might have been a member of M67, but it turns out that that hypothesis was disproven. It just happens to be that cluster exactly the same age as the sun. So Chick Keller asked me the question, what happened to the sun's original cluster? Didn't the sun also form in an open cluster, just like these stars we're seeing, and just like the cluster M67? And if so, where are the sun's siblings, they're called, the stars that formed along with the sun in a cluster? Well, the idea that's thought of today is that the original cluster that the sun formed in 4.5 billion years ago has been dispersed around the Milky Way Galaxy. So if we look at this picture, this is not actually a picture of the Milky Way, but it is a recreation of the Milky Way from data from telescopes. So we actually are in the plane of the Milky Way. So you couldn't actually see it looking down like this, but it's been recreated. And the sun is approximately like 2/3 out from the center of the Milky Way. And it goes around the Milky Way every 20, it's gone around 20 times in the last, during its lifetime, over 4.5 billion years. It takes about, it says 250 million years to do one orbit, and it's gone around about 20 times, we think. So other stars that might have been formed with the sun, if they were closer in or further out, they may have been going faster or slower. They also may have had gravitational tugs on them, pulling them away from the sun and dispersing them. So we think that the sun's cluster it had maybe between 1,000 and 10,000 stars initially, not a lot of stars. And so it wasn't very gravitationally bound to itself. And those stars gradually just got dispersed away by gravitational tugs, interactions with other nearby stars, so that our siblings are no longer apparent to us, right with us, going around the Milky Way. So in 2014, there was a paper published looking for solar siblings. And they claim in this paper by Ramirez et al., a lot of authors here from McDonald Observatory in Texas, to have found one solar sibling candidate. And the name of this star is HD 162826. It also has another name like HR 6669. So this next picture is showing just again an artist's rendition of this star relative to our sun. So even though our sun and the star are the same age, this other star is a little bit more massive. It's about 1.5 times the mass of the sun. It's 110 light years away, and it's hotter than the sun. But their arguments are that it is the same age and has the same chemical composition as the sun. And they particularly like looking at rare elements in the spectra to determine whether it was the same. And they said that this star has the same amount of yttrium and barium in particular as our sun. And we've looked for planets around the star, but no planets have been detected so far. So one of the things that's intriguing that I've read about solar siblings is if our sun and other stars formed in the same cluster, could we have shared any matter between the stars? Could meteorites from another orbiting one of the other stars have landed on our Earth? Could life have been seeded from life having formed in another star in that cluster? And so if we found so this is of interest, because if we find other stars that are our siblings to our sun, maybe they have a better chance than other stars of having life around planets around them. But so far, we haven't found any planets around this particular star. So the reason that they're really confident about this star being a solar sibling was that they did some calculations of gravitational forces on stars that were candidate solar siblings and tried to project back where would this star be 4.5 billion years ago. So most of the stars they looked at, all the stars on the top of this diagram here, they might be close to the sun today, but 4.5 billion years ago when that star formed, it was far away from the sun, according to their calculations, which I think are quite difficult to do and quite uncertain. So they found that was true of almost all these stars, except this star, HD 162. It's 110 light years away now, but when they try to project it back, they see that it never got very far away from the sun. In fact, it stayed, within 10 or 20 parsecs in some cases from the sun. And then they also looked at its velocity, and they projected that back in time. And it has matched velocity pretty closely with going around our galaxy to our sun. You can see here it almost had the same velocity back 3.5 billion or so years ago. So whereas these other stars they looked at, their velocities were much different compared. It wasn't staying with our sun. The relative velocities, they were getting much larger compared to these stars. So based on the dynamics and based on the element abundances, they think this is a really good candidate for a solar sibling. And this is the only one we know of so far that passes those two tests. So I'm going to go on now and tell you about this NASA Kepler data that my colleague in Poland acquired and asked me to look at. The Kepler spacecraft was launched in March of 2009, and its mission ended in November of 2018. But we've put up another satellite since then called TESS that is taking similar data. It's different, but in some ways, but still usable for stellar oscillations as well. High precision CCD photometry is used in this satellite. The purpose of it was to detect planetary transits or planets going in front of the star producing a little eclipse. And I've talked about that in previous talks at Peak. But it has a secondary mission to survey and monitor the variability of many, many stars, over 100,000 stars, for their pulsations, to try to understand what's going on inside the star for astroseismology. So the Kepler spacecraft basically looked at this place in the Cygnus Lyra region of the sky with its 21 CCD detectors here. It basically looked at that place without moving for 4 years. So we have 4 years of continuous data on those stars in that field of view. So this is a picture of the array, so you can see how big the CCD camera is compared to this person before it was launched in 2009. And then here's a picture of this third stage getting mounted to the spacecraft, and the mirror is up here in this round circular thing on top of the spacecraft, again, before it got launched. And when it was launched, it was put in an orbit not around the Earth, but around the sun. It is in the same orbit as the Earth, trailing the Earth, going around the sun. So, and it's basically lagging. So it's getting further and further behind the Earth all the time as the years progressed. So what's good about this orbit is that you don't ever get the Earth in the way. It can always point at this field in Cygnus, and it doesn't ever get obscured by the Earth having gone behind the Earth or having the moon in the way, for example. So this was picked deliberately to get this very long time series of data. So this is the field of view, again, of the 21 CCDs. And there are 2 clusters in this field, 2 open clusters, NGC 6811, and this one, which is the one I'm looking at, NGC 6819. So just this little tiny spot on this one CCD camera right down here. There is another cluster here, but it's right at the edge, and I don't know how much data they were able to get on that cluster right there. So why am I interested in NGC 6819? Well, it's 2.5 billion years old, 2.4 billion years old. Here is the isochrone, this line of constant stellar age that's through a bunch of the stars in the color magnitude diagram. So they fit isochrones. So I looked at 2.25, 2.55, and 2.4. And 2.4 kind of goes right through the middle of all the stars. And here's the main sequence turnoff, where stars have finished burning their hydrogen and they're coming off and becoming red giants over here. But look up here, there's a lot of stars that for some reason didn't evolve off the main sequence. They stayed on the main sequence. They should have become giants. they should have finished burning their hydrogen into helium by now, but they haven't. And these are called blue stragglers because they're straggling. They're not going over here like they're supposed to, and they're blue. They're a brighter, with a higher B magnitude than the rest of the stars in the cluster. So these stars happen to be at the right place in the color magnitude diagram and the right mass to be delta Scooty variables, which is what I am interested in finding. And if we can understand the interior structure of these stars because of their pulsations, we could maybe solve the mystery of why did these stars not go over here? Why are they still on the main sequence? The origin of these blue stragglers is not known definitively right now. We think that they could have undergone a mass transfer in their past from an interaction with a nearby star, or even had a merger with a star in the past. So if we can understand some more about the interior, we might be able to figure out if that actually happened to these stars. So why do we care? I'm going to go in a little bit about the pulsations themselves now. Why do we care about pulsations? Well, they, as I said, they give us information about the sun, about other stars, and even about the planets, because we can infer things about the size of the planet if we know the size of the star that we couldn't obtain otherwise. We can tell what's going on inside the star where we can't see it. We can determine the mass and radius of the star, even though we can't resolve the star. It just looks like a little point of light. We can use these pulsations to figure out the mass and the radius. We can figure out how large a planet would be that's going in front of the star. And we can tell more definitively what the age of the star is. So I've shown this picture before just to give you an analogy of what the sun and other stars do. Well, they vibrate in very similar ways to a bell. So here's a picture of a bell. And they can use Dopplergrams to figure out the frequencies of the bell. So this bell can ring in many overtones, many harmonics at the same time. So here's a bell, here's one of the harmonics, and they use this velocity measurement to figure out what parts of the bell are ringing. And you see there's parts of the bell going in and out, and then there are these node lines or these patterns on the bell. So this one has just a few node lines on it, and it has a frequency of 1342 hertz. And you can make a frequency versus amplitude diagram of the frequencies of this bell. And so here's the 1342 hertz frequency. And then if I look at a little higher frequency, you see that there's another mode here with more node lines. It's a higher pitch, and it's this red line, and that's the 1469 hertz mode. And then you can find another pattern here at 2605 hertz, and this is a high frequency, higher pitched mode. So the sun and other stars do very similar things to this. The stars I'm going to be talking about are these delta Scooty stars, and I'm also going to be talking about stars that are a little less massive than that, the gamma Dor stars. So this is a picture again of the main sequence where stars are burning hydrogen into helium, and this is luminosity versus temperature, with the cool stars off here and the hot stars over here on the left. And the sun in this picture is down here, burning hydrogen into helium. And solar-like stars are down here in this yellow circle. So up here at about twice the mass of the sun are the delta Scooty variables, and then in between them are these gamma Doradus variables. So the delta Scooty stars pulsate in pressure modes or acoustic modes, just like the sun. They're about twice the mass of the sun, and their periods are about 2 hours. For comparison, the sun's periods are about 5 minutes, so a lot shorter. And then there is this set of stars in the middle that pulsate in a completely different type of mode, and they're gravity mode pulsations, where gravity, like waves going on the surface of the ocean, bobbing up and down, is the restoring force for the modes. And they're about 1.5 times the mass of the sun, and their periods are longer, about 1 to 3 days. So, and these are so close together that you find stars pulsating in both types of modes at the same time, both the 2-hour one and the 1 to 3 day ones. So as I said before, for distant stars, we can't detect these very high frequency patterns like we saw in that bell, like this one on the left, where there's lots of node lines and lots of different places, patches moving in and out. So this is an L of 10, M of 5. It has 15 total node lines on it. Most stars are far away and we can't resolve this pattern in our telescopes. Maybe for red supergiants like Betelgeuse, we can start to get some idea of a pattern, but not for the most of these stars I'm talking about. However, if these patterns don't average out over the whole disk, like this picture on the left, this is an L of 2 mode. It has 2 node lines, and you see there's this big patch here because the star's tilted towards us, it's going in and out, and that's a different size than the smaller patch here. So over time, these two don't average out, and we can detect frequencies of this type of mode. So L of 0, where they're all radial modes going in and out together, L of 1, L of 2, maybe L of 3, we can detect with our telescopes using photometry like in the Kepler spacecraft. So just to orient you, I'm going to show you not a picture of an NGC 6819 star, but the data from a TESS light curve of a really bright star that they observed. It's magnitude 4.7. You could see the star naked eye in the constellation Gemini. And if you look at the light curve, this is a 27-day TESS light curve. And you see that the amplitude of the mode, the light, is just going up and down, up and down, up and down, around 5 parts per thousand, really fast. And there was a break in the data here. I guess they download the data midway through, and then they start taking data again. And then if you make an amplitude versus frequency plot, just like for that bell, you see the amplitude here and you see the frequencies of the modes here. Well, there's a whole lot of modes here, right around, between 10 and 20 cycles per day, or 2 hours, basically. 24 cycles per day would be 1 hour, 12 cycles per day would be 2 hours. And these are the delta Scooty frequencies. So this star has a lot of delta Scooty frequencies here, maybe more than 200 frequencies total. But this star also shows some of those gamma dwarf frequencies, these ones with a period of 1 to 3 or so days. So here's 1 cycle per day. This is actually a 3rd cycle per day, 1/5 cycle, 1/5 day, 5 cycles per day, a little bit higher. But you see that does also have some gravity modes. So this star is going to be really good to model and try to use all of this information to figure out what's going on inside the star. And what we'd like to do has been hard to do, because if I go back here, these frequencies don't really have much pattern to them. They're not equally spaced. We don't really know why these have the highest amplitudes and why these have lower amplitudes or heights. So we haven't been able to find the patterns we expect from theory. But in some delta Scooty stars, we're starting to find the patterns, just like we did for the sun. So here's some stars from Kepler data and from TESS data, where you see a lot of frequencies with almost equal spacing. Here's this frequency spacing, 6.75 microhertz, 7.2 microhertz. That's not all the modes. Some of the modes are not exactly in that equal frequency spacing, but at least we found a pattern. And the pattern can be compared with what we expect from our theoretical models. And these different spacings can tell us the average density of the star. So that's a nice diagnostic to have. And then also for the gamma dwarf stars with the gravity modes, they found not frequency spacings, but we expect equal period spacings. And so this star, we were able to find in Kepler data a lot of modes. We don't know why these amplitudes are all different. Some of them are high, some are low, but we were able to find a pretty much equal period spacing between these modes. And these period spacings and the slope of them tell us something about how fast the star is rotating in the core. So that's a really nice piece of information to get. Okay, so now I'm going to tell you about this data on this cluster. So our colleagues in Poland took this data or analyze this data. What the Kepler spacecraft did is that they zoomed in on the center of this cluster. This is by far not the whole cluster, just the very dense core of this cluster. With, you can see this triangular pattern here where there are a lot of stars. And Kepler had 200 pixels by 200 pixel field of view, and they basically took the data every 30 minutes. They integrated on the light and they stored the data for every pixel in this thing called a super stamp for 4 years continuously. So imagine having this data, a light curve point every 30 minutes for 4 years. There is no other spacecraft or no other data set like this for variable stars or photometry to get that much data continuously for 4 years. There were some gaps because some of the CCDs stopped working in the middle of the 4 years, but they would just rotate the field of, or the array so that the cluster would get back on a different array. So they managed to get most of it. And you can see this field is very crowded. So contamination of a light curve from one of these stars to the next is an issue. So these colleagues in Poland analyzed every star in this field. They picked out all the variable stars. They tried to put them in different categories, and they sent me what they thought might be the delta Scooty stars. And they also had to determine cluster membership, because some of these stars may actually be in the foreground, very closer to our sun, or they could be in the background away from this cluster. So they used some new data, Gaia Early Data Release 3. This is extremely new data on astrometry, looking at the proper motions, how these stars are moving in the sky, and their parallax, how far away they are from the sun, to determine, if they're all about the same distance and they're all moving in the same direction, they're probably cluster members. So they had to rule out a lot of stars that weren't cluster members. So I'm going to show you now just 5 stars that we picked out that we think might be delta Scooty or gamma Dorada stars. And it's going to be hard to tell. Some we can tell easily, some it's hard to tell. So this particular star, you see how faint it is. This is the catalog number. It's magnitude 15, very faint. You need a telescope to see that. It's in that blue straggler region, which is exactly where I wanted to find stars to understand why they're still there. Why didn't they evolve off and become red giants? And it had, here's a light curve. And I zoomed in, I didn't show you 4 years because it would just be a complete blue. Actually here, you couldn't tell anything. But I zoomed in on this with 10 days of the data instead of showing you all 4 years. And you see there's something going up and down here and kind of a low frequency, but there's also some high frequency stuff. And then here, if you look closer in, this is only 2 days, you can zoom in on the high frequency. And then if you do a amplitude versus frequency plot, like for the bell, you see a whole bunch of modes here, about 16 cycles per day. And this is right where you would expect the delta Scooty variable stars to have frequencies. So this is definitely a delta Scooty star. It has a little bit of low frequency stuff here. You can see down here. This could be the star's rotation. Like there could be a spot or a sunspot or some other asymmetry in the star, and that could be causing at least this higher amplitude one. So it could be a rapidly rotating star. So the second star I'll show you, also magnitude 15. It's also in the blue straggler region of the diagram. And here I've only zoomed in on 50 days because instead of an even smaller number, because it has some variability, but it's quite low frequency. And if you take a Fourier transform of that and look at amplitude versus frequency, most of these modes we find are only between half and 1 day. Well, this could be a reasonable number for the gamma Dorada stream mode pulsations, reasonable frequencies. But other people have looked at this data and have conjectured instead that these are star spots going around and coming and going, and probably even star spots that go around faster in one latitude of the star than the other, just like our sun goes around faster at the equator than at the poles. So it's not clear what these are. These could be gamma door modes. These could be star spots. So more work is going to be needed to understand that. And I did look at very high frequencies, and we did find one mode around the Delta Scooty range. So this could be a Delta Scooty star, but with just one mode, it's hard to call it a Delta Scooty star. It'd be better to have more than one mode. Okay, here's the third star we looked at. This one has, I've looked here 20 days zoom in on the light curve, has pretty low frequency pulsations compared to the Delta Scooties. And if you look at the frequency versus amplitude, there are a lot of modes here that go between 0 and 5 cycles per day, a lot around 2 and 1 cycle per day. So I think this is a really good candidate for a Gamma Doradus variable star, Delta Scooty star. And this star was a mystery. Well, no, this isn't as much of a mystery as the next one. This is a magnitude 13 star. It's also in the blue straggler region. It has 2 or more close frequencies that are kind of beating against each other, interfering constructively and destructively to make this pattern, which is really pretty pattern here on its light curve. This is a 5-day light curve. And if you look at the amplitude versus frequency, there are a lot of modes right at 12 cycles per day. This is the 2 hours, the Delta Scooty mode period exactly. So this is definitely a Delta Scooty star. But if you zoom in really close on these low frequency modes here and even go up higher, you can see there are modes, they're very low amplitude, even at higher frequency and some at lower frequency. So this could be a hybrid star, a hybrid Gamma Dor Delta Scooty star. And this star was difficult to analyze because remember I told you there's a possibility of contamination. This cluster is so dense that the stars are very close together, so we can get light contaminating one light curve from another. And in fact, that light curve was contaminated by this binary star, eclipsing binary right next to it. So you can see here this star very nearby. It's going, this is a binary star and 2 stars going around each other. And when one star gets right in front of the other, you see the light amplitude drops out. So this is an eclipse. That star is getting right in front of us compared in our line of sight with the sun. So you have this eclipse and it happens every 3.5 days. And so if you did an amplitude spectrum of this, well, you get this funny pattern from the eclipse, but you can see this 12 cycle per day signal, and that's from that other Delta Scooty star I just showed you. So that star was contaminating this one worse than this one was contaminating the other. But you have to be aware of this and try to rule out signals from nearby stars when you do this analysis. And finally, I guess here's the mystery star. This star is not in the blue straggler region. It's near the main sequence turnoff, closer in temperature to our sun. Our sun is 5,700 Kelvin. This star has, again, 2 close frequencies that are beating against each other. So you see this pattern kind of like the last star, only a little bit less complex. There's only really 2 big amplitude modes. And we looked for more modes, and all we could find in this star were those 2 modes plus some harmonics of those 2 modes. There's some harmonics here, and there's some that are so low amplitude you can't see. And there are even these 2 subharmonics, which seem odd. You shouldn't really see things that are half the amplitude of the big amplitudes. So there's a lot of speculation in the literature about what this star is. It was even looked at in X-ray and ultraviolet, and they found a lot of activity in the UV and X-ray. So this is called an active X-ray binary star, X9. It's labeled in this paper. Here's the main sequence. You see it's not quite at the turnoff, but it's moving off here. It's thought to be a binary at least. With one star that's chromospherically active, has sunspots, maybe has flares. But understanding why it makes this pattern is going to be difficult. So to conclude, Despite being in the same cluster, having the same location in the HR diagram, every one of the stars we've looked at are very different. And of the 5 cluster member stars that I'm looking at here, we found 2 definite delta Scooty stars, 2 stars that have lower frequency variability, could be gamma dwarf stars, could be rotation in spots, or even this other kind of gravity mode pulsation called a Rossby mode, which has got a characteristic signature that hopefully we can find in this data. And then we found this one star that has those 2 close frequencies in their harmonics. So in addition, my collaborators in Poland sent me 8 other stars. They think that stars are non-members based on this recent Gaia data. But in older literature, it says that these stars could be members. So more work maybe needs, some of these stars may end up going into the member category, but we still need to analyze them. And we found 4 more delta Scooties and 4 more of these gamma Dor looking stars. So what am I going to do in the future? Well, I hope I can just write up the data and the analysis on these stars, and then maybe a follow-on paper model the evolution and pulsation of these stars, starting with the delta Scooty stars and the ones that are blue stragglers, and using these constraints that I know the age and I know that they should have the same abundances. All the stars should have the same abundances of elements. And I'd like to try to find some frequency or period spacings, because maybe that would be useful to find more about the mean density and the internal rotation rate. And these stars are so faint, it's maybe going to be hard to get more data, but possibly some spectroscopy or color photometry might help to sort out whether these signals are gamma Dor pulsations or spots or rotation. Okay, I'm going to stop now. Thank you for listening. I'll stop sharing my screen, I guess.
Actually, you can keep sharing it for a minute if
Okay,
you want.
sure.
Some of the questions may be related to some of your slides. And while we're waiting for some more questions to arrive in the chat, let me remind folks that you can type questions into the chat and I'll relay them to Joyce. A question that I have, and partly because I'm not very familiar with these types of stars, on the blue stragglers, has anyone done any modeling? Are there ideas out there for why they're lagging along on the main sequence, like mass transfer to a binary companion or something like that? Have they come up with some reasons for that?
Yes, there are several stars that are suspected blue stragglers that are fairly bright that we've had Kepler and test data on. And some students have even looked at individual stars for their PhD. They do think that the astroseismology is consistent with some kind of a binary merger or mass transfer event. So the problem with the mass transfer, I remember hearing this talk where this guy gave a convincing argument that it was mass transfer, but then the questioner said, well, is there a binary companion? Where did the mass come from, right? And they didn't have an answer. They couldn't find the binary companion, but maybe it had already merged into the star. So when I first started, like 30 years ago, there was some thought that these blue stragglers were caused by extra mixing in the core of the star. Either the core was spinning very rapidly or some process was going on to keep mixing fresh hydrogen into the core, so that would keep it living longer. But I'm seeing more papers lately that are discarding that and thinking it has to be a binary merger or a mass of some kind of a mass transfer event.
So the in this slide that you have, looking for, modeling some of these constraints on the stars, you might find out something about this internal rotation rate and perhaps could speak to this question of mixing.
Yes, absolutely. Yeah. And something about also the density profile. If it's really dense in the core, what does that say about when the mass transfer or the merger happened, or if it's all homogenized, for example, that means maybe it's happened recently, the merger. So there are questions like that you could maybe answer. I have not tried yet, but it's exciting to get this data though on blue stragglers.
All right, very good. Just for the benefit of some of the people we have watching, I don't know how familiar with everyone is uh, with HR diagrams and the color magnitude diagrams. Some people I see have gone to so many of these peak talks now over the last few years that they probably know more about it than I do. But for those who may not, could you briefly talk just a little bit about what the HR diagram is and what it's showing?
Um, yeah, I'm wondering if I have a better slide, like with all the pulsating variables on it. Let me see if I kept it. This one, I kind of like this one. Is this okay? Can you see it?
Yes.
Okay, so this is basically a Hertzsprung-Russell diagram, and it just doesn't just have the clusters on it. It doesn't just have the delta Scooty stars on it. It has a lot of stuff on it. So this is the luminosity or the brightness of the star on a log scale on the left axis, and on the x-axis here is the log of the effective temperature or the surface temperature of the star. And on this diagram, we have the cooler stars are on the right and the hotter stars are on the left. So stars start on this dashed line here, burning hydrogen into helium in their core. And this is what's called the main sequence. And as stars finish burning their hydrogen, these are stars of different masses. So our sun started out at 1 solar mass, it's down here. These SPB stars are 4 or 5 solar masses. So they start about here. Beta Cepheids could be up to 20 solar masses, and they'll start up here. So the stars that are higher up, they're more massive, and they are actually, there's more pressure and more higher density in the core, and they actually can burn their hydrogen into helium quicker. So they end up living on the main sequence. Their lifetime is much shorter, and they evolve off to the right here. Whoops, I'm sorry, I messed up. They're evolve off to the right, and they will become red giants. They'll go across quickly up the red giant branch. Then they'll come across briefly, and well, maybe about 1/10 of the rest of their lifetime, and they'll burn helium in their cores into carbon, oxygen, and then they'll again, after that's exhausted, come up and go on the asymptotic giant branch. Some of the stars that are really massive will become supernovae. And some of these will actually, I guess the 10 or 20 solar mass stars can become supernovae at the end of the asymptotic giant branch. So let's see, what else can I tell you? Stars, some of these lower mass stars, after they finish being red giants, they evolve across the HR diagram and come down here and become white dwarfs. So these stars are, this is the white dwarf cooling sequence. So the stars come across and they've exhausted all their fuel. It's just a bare core of carbon or oxygen, or maybe neon magnesium if it's massive enough, and they will basically cool for a very, very long time. Some of the stars down here have been there since the universe first formed. They're 12 or 13 billion years old. They've cooled down back over here. So what else did I miss, Rick?
Oh, that's pretty good. I think that's a great overview of these diagrams. We might mention, I'm not sure, you mentioned that the stars in the upper right would be red giants, and you can see why they're called that,
Yes.
because they're much cooler. They're over to the right of the diagram, but they're also very bright. They're up at the top of the diagram. How can they be cooler and still be brighter? Well, the only way is if they're much larger. And so that's why they're called red giants. But thank you. Yeah, that's a great explanation, I think, of that diagram.
This picture is focusing on all the variable star types that exist. And so, we have our different Gamma Dor, Delta Scooty. There's Cepheid variables here. The Myra variables, their periods are about a year. They're really long period variables. And then these white dwarfs, I think their periods are minutes again, pretty sure. Yeah, these different kinds here. So what's really nice is that all these stars, if they vary and pulsate, we can do this astroseismology and understand their insides, which it's a sort of a relatively new field. In the last 30 years, we only really knew of several classical variable star types, but being able to make use of all this data is really exciting.
Yeah, that's fantastic. It'll be interesting to see as more people are able to model the data that's now coming out, what they find out about these stars. Okay, I'll make one last call for questions. I don't see any more questions. Oh, well, now I do see some questions. You're not off the hook yet. It is kind of interesting. This is the first Zoom talk I've been on since Zoom was updated to slow down instead of making your voice choppy if it had trouble with the bandwidth. Instead of doing that, it slows it down. So you're still talking about stars. It's just that the volume goes, or the pitch kind of goes down, and it goes very slowly, and then it comes back up again. And I wanted to mention to people that that's not you emphasizing what you were saying. That was Zoom.
Okay.
But anyway, that's an interesting effect.
Maybe I should have turned off my camera.
That's okay. I think it was quite understandable the way Zoom handles it now. Here's another question. What are the chances, that is the expected percentage, of interlopers among the blue stragglers? Not sure what that
Oh, yes, there are. I think I do. For this cluster, when they originally were looking for blue stragglers in this cluster, they said, "Oh, we found 29 blue stragglers," and then they tried to figure out the cluster membership, especially with this new Gaia DR3 data, and they found out most of these blue stragglers were not cluster members; they were interlopers. They had come from someplace else in the Milky Way Galaxy, and they just happened to be in the field of view of the cluster. So, yes, there's not 29. There may be 5 or 10, right?
Okay.
They're cluster members. Yeah.
Good to know. Okay. And Doolin's asked something. I think you actually have a slide that talks about this. Can the distance between the sun and its proposed sibling, about 110 light years, be calculated backwards in time to see their separation when the sun was created?
That's exactly what that paper did.
Yeah, could you show that slide again?
Yeah, we'll go back. And I read their paper, but I am kind of skeptical that they could do this so accurately, especially in 4.5 billion years, because you don't know what the galactic structure is that accurately 4.5 billion years ago. Okay, so here's the picture. So 0 is the current time, and 4.5 billion years on this picture is on the far left. So the left picture is distance, and the right picture is velocity compared to our sun. So then what they did is that they assumed a gravitational potential that included the galactic bulge, the disk, and the I think the spiral density waves from the spiral arms. And I think there's one more term for the gravitational potential. So what bothers me is that those things are changing with time too. So how to take that into account? But they use that gravitational field, and then they look at where the sun is and where this HD 162826 star is, and they move them with respect to the gravitational tugs they're going to feel. And looking backwards, it looks like here's velocity. It looks like here's our velocity with respect to that star right now. What is it, about 5 kilometers a second going around the Milky Way? So in the past, it was bigger, 10 or 12 kilometers a second, and then the velocities seem to get closer together and then further away again. But they never got terribly different. So, and there's some cases, there's these periodicities in here where they got to be almost the same, where the velocities are almost matched with the star and the sun. And then this picture over here is showing distance of that star to the sun. And again, you see these funny periodicities where it probably orbits around or gravitational potentials that are aligning as the star, as our star and the sun are going around. And sometimes we get closer to that star. Right now, they said 110 light years. These are parsecs, so it's hard to, you have to translate. But it has been closer in the past, and it never gets very far away. So that's why they think this is a good candidate for a, they also thought the star 83 whatever here was a candidate, but the distances were always pretty far apart. The velocities are matched pretty well, but the distances on the left were pretty far apart. So yes, that's what they did. They tried to calculate it backwards.
Yeah, that velocity curve kind of reminds me of what you might see. I haven't thought very hard about this, so maybe this isn't true. If you had the sun orbiting the galaxy and another star kind of weaving in and out of the sun's orbit as it goes around the galaxy in terms of velocities, that's the kind of curve I would expect perhaps to see.
Right.
The one on the left with the distances, so, you would hope that the distance would get, I mean, it's nice that it doesn't get any farther away like the others do. But it would be nice if that distance kind of almost went to zero at the 4.5 billion years ago. But the uncertainties you were talking about in those gravitational fields and the fluctuations and the things that they really they don't have the information to correct for properly in their code would introduce errors that might be at least that large. So it makes sense that they're happy if it just stays at the same distance.
Right. Well, I guess you can certainly, here's the paper from 2014, and it's a nice paper. It's very readable. So I would certainly recommend, reading it and let me know what you think. So it has a lot of nice background about what they think that the sun's cluster was like and how they constrain that. Why do they think it's between 1,000 and 10,000 stars? Just things like that. It's got a lot of nice explanation.
Good. All right. Okay. Well, those are all the questions that came in from the viewers. Joyce, thank you so much again for sharing with us tonight, and especially all of the work that you have put into this and giving us an idea of what's coming up in the future for the work that you're going to be doing with these stars.